Hi, my name is Isabel Alvarado, and with my team, Vianney Salazar and Ana Sofia de la Cruz, we're going to talk about the case of spatial patterns of soil degradation in Mexico. Soil is a critical, non renewable natural resource. Once degraded, the costs and difficulties of recovery are immense. In Mexico, recent data indicates that 64% of soils are degraded to some degree. This degradation poses a major threat to global ecosystems conservation by reducing food production potential and leading to desertification and erosion. Within the realm of soil quality modeling, this study addresses a significant gap. While technical reports on degradation are numerous, they often ignore spatial distribution aspects. Understanding whether soil degradation is random or follows a specific pattern is vital for developing evidence-based conservation strategies, identifying causal agents and conditions that induce erosion to design effective prevention programs, and providing a strong background for the operation of large-scale land management programs.
The main objective of the study was to analyze the spatial pattern of soil degradation in Mexico and determine whether this pattern is random or spatially correlated. The researchers aimed to 1. Test the hypothesis that soil degradation follows a non-random spatial autocorrelation pattern. 2. Identify whether degraded areas tend to cluster geographically. This indicates if areas with similar degradation levels are located near each other. 3. Generate information useful for designing soil conservation strategies and environmental policies. The study was conducted because a large portion of Mexico's soils, about 60%, are degraded. Soil degradation threatens ecosystems, agricultural productivity, and leads to issues like erosion and desertification. Also, previous research focused more on technical descriptions but lacked spatial analysis, limiting understanding of patterns and causes. Now, I'm going to be talking about the methods utilized in this study. It used geostatistical and spatial analysis techniques to model soil quality, in this case, degradation levels. The methodology can be divided into three key components. First, data collection. The data came from CONAFOR, a study from 2006, in the form of a shapefile. The dataset included 16 and 40 ecological units across Mexico. Soil degradation was classified into four levels: slight, moderate, strong, and extreme. This classification was based on loss of biological productivity. Second, spatial autocorrelation. This was the main technique used for soil quality modeling, and it was Moran's I coefficient. It evaluates whether similar values are clustered, dispersed, or random in space. The values range from -1, which is negative correlation or dispersion, 0, which is random distribution, and +1, which is a positive correlation or clustering. And third, they use graphical analysis, which are divided into two categories. The first one was Moran's scatter plot, which shows the relationship between the value at a location and the average value of its neighbors, and it also helps visually confirm spatial autocorrelation and local indicators of spatial association, or LISA, which identifies local clusters and spatial patterns, and classifies regions into categories such as high, which are highly degraded areas that are located near other highly degraded areas, low, which are low degradation clusters, and high-low or low-high, which are spatial outliers.
About the results showed that the soil erosion in the study area ranges from low to moderate levels, with values between 0 and 1.35 tons per hectare per year. This indicates that although the erosion is present, it is not uniform across the entire region. The highest erosion rates were found in tableland areas. This is mainly due to steeper slopes, low vegetation cover, and limited land management practices, which make the soil more vulnerable to being carried away by water. On the other hand, the lowest erosion values were observed in basins, alluvial terraces, and wadis. These areas tend to have flatter terrain and, in some cases, more vegetation cover, which helps protect the soil and reduce erosion. Additionally, the soil showed moderate susceptibility to erosion based on the erodibility factor. A clear trend was identified. Erosion tends to increase as slope increases and decreases when vegetation cover is higher. Overall, the results highlight the importance of the topography and the vegetation in controlling the soil erosion in the region.
The study concludes that soil degradation in Mexico is not random, but follows a statistical robust possessive spatial correlation pattern. Using Moran's coefficient, the researchers determined that the model synthesized 42.8% of the global linear correlation structure among degradation degrees. Through, through the local indicator of spatial association, we identify clear clusters. Highly degraded areas surrounded by similar zones are prominent in arid states like Baja California and Nuevo León. Areas with slight degradation are common in La Sierra Madre Occidental and the Central Highlands, often linked to dense forest coverage. These are frequently encountered in the tropical regions near the Gulf of Mexico. This finding demonstrates that incorporating the spatial dimensions is vital for improving our comprehension of soil erosion. By identifying these associations, we can accurately direct soil recovery and erosion control activities to the regions where they are most needed. Moving forward, further research is required to identify the specific underlying variables, biotic or not biotic, that drive these spatial patterns.